Okay, let's get started. So let's sort of look at our schedule. So first off, I've been having these tables on my announcement slide, and this one's new. This one's a totally different one. But the nice thing about this table is this is the end. This is it. We are done. That's our last lecture. So first off, let me get this passed around. So let's look at our schedule. So exam 2 is still being graded. My goal is to get that back to you next week. Now I'm not going to be here on Tuesday. What I could do is do an online lecture on Tuesday and then give you the 15th off. But I was going to give you the 15th off anyways. So here's the thing. After beam deflection, our next topic is stress analysis and Mohr circle, and it's one of the more intricate and, I don't want to say complicated topics, but it's one of the more famous ones in deformables, and it requires some attention, and I don't want to do that online. I would rather do that in person. So the analysis of stress and Mohr circle is really sort of our final topic before buckling. Combined loading and pressure vessels are sort of just kind of applications of stress analysis and Mohr circle. So the combined loading lecture is really one that we can do online because there's not a lot of new stuff in that lecture. It's a lot of sigma equals P over A. It's a lot of sigma equals My over I. So I can do that online quite easily. So we'll do the combined loading lecture online. And there's a homework number 7 that encapsulates stress analysis and combined loading and pressure vessels, but it's not due till after break. So you can just watch it at some point between when you're working on that assignment, and I think it'll be fine. Honestly, depending upon where we get with Mohr circle and stress analysis, that's probably going to be somewhat of a short video. So when we come back, we'll do pressure vessels, then we'll do buckling, which I have buckling will take 2 lectures, but really it's only going to take maybe a lecture and a half. If we book it, we might be able to get it done in one day, and then this day we might take off, but we'll see. And then that's it. That is mechanics of deformable bodies in a nutshell. So your final will have beam deflections on it. It'll have stress analysis and Mohr circle and all the applications, and then buckling, and that's your final. Sound good? Okay. Speaking of homeworks. You all now have the grades for homeworks number 1 through 5. Homework number 6 was assigned today. It is a short assignment on beam deflections. There's 2 problems, so it's not that big. It's due Tuesday, November 13th. Okay? What will happen on November 13th is I'll give you homework number 7, which won't be due till well after Thanksgiving break. And then you'll get homework number 8. I think it's on the 29th, and it's due on the 6th. And then those are all your homeworks for the semester. So that's mechanics of deformable bodies. Any questions? So again, we won't have class on Tuesday. One final thing, I'm probably going to end class a little early today. So I'll probably, if it gets to like 8:55 and I'm still talking, raise your hand and go, you said you were going to end class early. I get carried away. Shut up, Dr. Mike. You said to leave. Let's sort of recap where we left off last time. So I know it's been a while, so especially when we have exam reviews and all of that. I'll start here because I think this is sort of a nice way of summarizing. So in our last topical lecture, we were looking at the differential equation for beam deflection. The second derivative of deflection is M over EI. And we had derived that, in previous lectures, so I'm not going to, go through that. But we started looking at, well, how do we solve this differential equation? In other words, how do we determine expressions for the deflected shape of a beam? Well, the most direct approach is to just integrate. If the second derivative of deflection is M over EI, then the deflection is just integrating that M over EI term twice. It yields arbitrary constants, so we have to solve for those constants utilizing boundary conditions. So, excuse me, if you have a roller or a pen, you know that the deflection equals 0 at that location. If you have a fixed support, you know that the slope equals 0 as well as the deflection at that support. Again, you don't have to worry about the frames and stuff on the right because we're not going to deal with frames in here. For beam deflections, particularly if you're looking at US units, and I'll say this about US units and SI units, really my advice to you when you're looking at deflection calculations is when in doubt, when in doubt, get everything into a consistent unit system. And what I mean by that is, so if it's SI, put all your forces in, let's say, kilonewtons, and put all your distances in, let's say, millimeters. So you might have a beam that's, you know, 6,000 millimeters long. Like, that's fine. Keep it consistent, okay? And that will generally reduce the error. What I'm showing you here is a very special case. I mean, we are in America, and we typically use US units for a lot of engineering computations. So if you are expressing a member length in feet, and you need a deflection in inches, and you have a modulus of elasticity in KSI, and so on and so forth, deflection conversion factors are pretty easy to derive. If you're dealing with deflections, your conversion factor is 1728. If you're dealing with rotations, your conversion factor is 144, but mathematically, if all you use is 144, that's going to give you a rotation in radians. Personally, I'm a degrees guy. I like to see rotations in degrees. You're talking about rotations that are particularly small anyways. So I don't know. I just tend to think degrees are a little easier to see in your head. So I would recommend taking your rotations and then multiplying them by 180 over pi. Which, by the way, if you're doing SI units or even US units where everything's consistent, if you don't apply some unit conversion, if everything's in consistent units, when you compute a rotation, it will by default be in radians. So the 180 over pi, I still recommend that you throw that in there to get that into degrees. And so what you've got here in the box is a pretty nice little summary of what you need for conversions. Deflection 1728, rotations 144 times 180 over pi. And then this is the problem that we did last time. We kept it symbolic, and that is traditionally a lot of times the case when you're looking at deflections. Now I believe our next problem is not symbolic. We're going to do a little bit of a numeric problem. Now, look, you're doing integrals. There's going to be some symbols in there. You're going to have to deal with that. But the nice thing about what we did with example 25 is that when it was all said and done, let me pull this up. So here is our example. We determined our moment function here on the right. We then integrated twice, you know, breaking out the old Calc 1 skills, and then using boundary conditions to determine what C2 and C1 were, and then, you know, here's our function, so we have y of x is this. It's a little bit more work, I think, to derive a function in terms of variables. You know, you got a bunch of w's and l's and e's and i's all over the place. However, it's much more useful because now we can determine the deflection in a simply supported beam subjected to a uniformly distributed load for any beam, for any length, for any load. And it doesn't even matter if it's SI or US units. Everything's consistent. So, or not everything's consistent. Everything's there. So it's a little bit more of a useful expression. So it's just sort of my soapbox, you know, mention of that. Everybody good? Now what we're going to do is example 26. Example 26, we're going to determine or use either the direct integration method or the double integration method in order to determine the maximum slope and deflection of the beam shown below. Now, this is engineering. It's not math, so I think we can use a little bit of common sense. And what I mean by that is, here's the beam subjected to a load. I would argue that the beam is going to deflect something like that. Well, I know. So where is the maximum deflection? It's at B, right? Where is the maximum slope? Where is the point where the angle changes the most? It's at B, right? So we don't need to, you know, do first or second derivative tests to determine maximums and then evaluate your range. We don't need to do any of that. We can just look at the beam and know that's where the maximum slope and rotation is. We don't need to make it complicated. So all I'm going to do is I'm going to define the the function and just plug in, for where B is. I'm just going to keep it simple. Now, I do want to make a specific point. I'm going to do something a little weird on this problem, and I know my structures folks are well aware of this, but just bear with me for a second. All right. This needs to go down a bit. Okay. What I've got here, I just sort of repasted this as an image. Okay. I'm just using this for the sake of discussion, so don't worry. Just watch up here for a second. Let me ask you a question. Is this beam here on the bottom going to deflect any differently if I do that to it? In other words, if I take the beam, instead of the beam with the fixed end here and the load over here, what if I just flipped it? Is this the point going to go down any more or less? It's the same beam. In other words, here's the beam. Instead of me looking at it like this, I'm looking at it like this. It's the same beam. Okay? The reason why I do that is because when in doubt, when you're doing beam deflection calcs, and this is true if you're trying to define moment functions or anything like that, generally what is easier from an algebra standpoint is to define your origin where your free end is. So if you put the origin here and say this is the x-axis and this is the y-axis, you will generally make your life easier from an algebra standpoint, guaranteed. Okay? So the reason why I mention that and why I do that with this problem is because the way that this problem is, hold on, delete this stuff. Come on. I'll worry about it later. What I'm going to do with this problem is I'm actually going to define the origin at B, and the axes are they're going to go in the opposite direction. I'll draw that here on this so it's a little easier to see. So I have example 26. So what I have is I have a beam that looks like that. And this is 10 kips. How long is the beam? Does anybody have that on hand? 20, how much? 24 feet. Okay. So what I'm going to do is I'm going to define my coordinate system such that this is the y-axis and this is the x-axis. And so what I'm going to do is when I cut a section and I look towards the origin, my section is going to look like this. And then this dimension is x. And what I'm after is this unknown moment inside the section. Okay? The nice thing about, and here's the reason why defining the origin at the free end usually makes your life a little easier from an algebra standpoint. When I cut a section here and I look to the right, all I see is this 10 kip load at the free end, right? But when I cut a section and look to the left, what do I see? I see this fixed end right here, right? So if I were to cut a section and look to the left, it would mean that I would need to go through, determine my support reactions, and all of that. And what ends up happening is your moment expression ends up getting a little longer. You have more terms to integrate, more stuff to deal with, and it's just a pain. Now, let me be absolutely crystal clear, okay? Whether you cut a section and look to the left or look to the right, physics doesn't change. You're having the same response at that point. However you define your math or your equation doesn't change the actual response. I'm just saying it makes your algebra easier in the long run. If you put your origin at the free end and always look towards the origin when you cut a section, you'll always have an easier time. So if I sum moments here at the cut, if I sum moments at the cut, okay, I've got M going this way, and I have 10x going this way. Is everybody okay with that? Because they're both going in the same direction. Moments going like this, 10x is going like that. So what ends up happening is I have M plus 10x equals 0. So I actually have a negative 10x. Now that should make sense because look how the beam is going to deflect. It's going to deflect in a frowny face. It's not going to be smiley face. So all of the moments are going to be negative. Okay? Everybody all right with that? Now, if you're okay with that, the only thing left to do, and I want to do this now before I start getting into the problem, is I'd like to define some boundary conditions. Okay? What I mean by that is, remember, when we integrate, we're going to have two arbitrary constants of integrations, so we have to have two known quantities in order to be able to solve for those constants of integration, right? Okay? So, help me out. What is the x value, let's say right here, like at this point, what is x? X equals what? Okay, so this might be x equals 12. So this is x equals what, 24? Okay, so let's list our boundary conditions over here on the right. Let's see, boundary conditions. All right, we're going to need two of them. Okay, so for both of them, I propose that they're going to occur at x equals 24 because that's where my support is. Okay, so somebody tell me one of them. What is going to be the case at x equals 24? Tell me one of them. The slope is going to be 0, and what's the other one? The deflection will be 0. So at x equals 24, we know that the slope equals 0, and we know that the deflection equals 0. And so those are the boundary conditions that we'll need in order to evaluate this problem. Pretty simple, right? It's not that challenging. In fact, cantilevered beams in scenarios like this tend to be easier than simply supported beams. So. Sound good? All right. So let's do this. Direct integration, right? So we have, how do we write this last time? We said the second derivative of deflection is m over EI. So EI times the second derivative is m, right? Which in this case is minus 10x. So in order to determine EI times the first derivative, which is EI times the slope, we're going to integrate once. So therefore, EI times the first derivative, which is EI times the slope, is the integral of minus 10x dx. Okay? So, what is that? Minus 5x squared. But hold on, what's plus c? So, minus 5x squared plus c. And we'll call that c1. Because we know we're going to have an arbitrary constant of integration again. However, could we go ahead and solve for c1 right now? I mean, here's our expression for EI theta, right? And what do we know from our first boundary condition? We know that if x equals 24, that theta equals 0, right? So why don't we evaluate that? Let's look at boundary condition 1. So EI times 0 is minus 5, 24 squared. Actually, let me write that. Plus C1. So 0 equals C1 minus what? What is 24 squared times 5? Say it again. 5,080? Okay, hold on. 2880, okay. You got outvoted, man. All right, so therefore, C1 is 2880, and EI, so I'll write this like this, EI times theta is 2880 minus 5x squared, right? That's pretty straightforward. So that's simple. Now, what did this problem state that we needed to go ahead and determine? We needed to determine the maximum slope and the maximum rotation. So where does maximum rotation occur on this problem? At B. And what is the x value at B? 0. So therefore, and I don't want to, take this to a new screen, so I'm going to sort of put this over here. I can say, therefore, EI times theta max is 2880 minus 5 times 0 squared, which is 2880. So therefore, theta max is 2880 over EI. So that's, what do we have? We have 2880. And then what was E? 4,000. And I is 8,000. And this is a rotation, right? So I propose for a rotation, throw in your 144, throw in your 180, throw in your pi. And so what does that come out to be? It's not mine. 0.743. Do I have a second on that? So again, just recognize what that means, right? Here's the beam deflects. That point at the end, we know it shifts down some. We don't know how much yet because we haven't done that yet, but we know it shifts down and we know it rotates. How much does it rotate? It rotates about 0.74 degrees. Honestly, I think that's a little easier to conceptualize in your head than radians. I'm just a degrees guy. So and that's one of the other reasons why I leave the conversion factor 144 times 180 over pi. If you want radians, just remove the 180 over pi. I don't like multiply the 144 and the 180 out. I think it's a little easier to see what's going on. Sound good? Not too bad, right? So now we only have one more step to do, and it's pretty much just the continuation of this. We need to integrate one more time. So does everybody have this? Okay. So we know that EI theta is 2880 minus 5x squared. So EI y, we have to integrate that. And so that is, so the integral of 2880x minus, what's the integral of 5x squared going to be? 5 over 3x cubed. There we go. So, missing anything? Plus C2. And now that we've got this, utilize our second boundary condition. And so what our second boundary condition states is that if you plug in x equals 24, you get in a deflection of 0. So we have EI times 0 is 2880 times 24 minus 5/3 times 24 cubed plus C2. So therefore, C2 is going to equal 5/3 24 cubed minus 2880 times 24. And so what does that come out to be? Negative 46,080, like that. Do I have a second on that? There we go. So therefore, EIY is 2880x minus 5/3 x cubed minus 46080. All right. What's left? You tell me. And what do we do to that for that? Plug 0 in. There you go. So EIY max is going to be 2880 times 0 minus 5/3 times 0 cubed minus 46080, which equals minus 46080. Why the minus? Because it's going down. So, pretty simple. And just plug and chug. Remember, this was 4,000. That was 8,000. Did I get that right? And then, what are we missing? There we go, our conversion factor. And so, minus 2.49. Do I have a second on that? Okay. So therefore, if we wanted to summarize our problem, we could say that Y max is minus 2.49 inches and theta max is, what was it, 0.74 degrees. Okay, now the one thing I want you to make sure that you're aware of is why we care about those numbers. You're like, great, it goes down 2 inches, it rotates a little bit, who gives a damn, all right? The big thing to keep in mind is, you know, what you're designing. Okay, now whether or not you're a civil engineer or a mechanical engineer, it doesn't really matter. You're going to be designing systems that have to perform under certain tolerances. So for instance, if you're a civil engineer and you're designing a beam in a building, well, you obviously don't want the beam to be stressed too much, because if the stresses get too high, the beam's going to fail, okay? But at the same time, you also don't want the beam to deflect too much, and they're not the same thing, okay? For instance, if we're looking at the floor beams above us that are holding up the floor above, you know, right here, obviously we want those beams to have enough strength. We want their stresses to be below a certain value, you know, factors of safety and all that. But it is very possible that we could check the stress on this beam, and the stress is fine, but it's deflecting 2.5 inches, and the deflection is too much, okay? It's the same thing if you're designing an airplane wing, or, you know, if you're, we've had problems like this before when we looked at, for instance, for you mechanical engineers, we looked at torsion, right? And there were instances where we had a torsional shaft where we had to limit the shear stress to 10 KSI, but we also had to limit the angle of twist to 2 degrees. So based on those two limits, which controls? And from there, it wasn't the same story, right? Sometimes the stress is controlled, sometimes the angle of twist is controlled. Well, it's the same thing with beams. Sometimes the stress is controlled, sometimes the deflection is controlled. Okay? So it's the same idea. All right? Fortunately, you know, for most basic loading scenarios, it's not hard. So let's say, just for sake of discussion, let's say 2.49 inches was too much deflection. What would you as the engineer do to this beam? How would you fix it? Give me some options, because it's not one answer, there's a few. Make it deeper. And so analytically, what does that do to these numbers? So it bumps up your I value. So one potential option is to increase your moment of inertia. And you're saying to do that by increasing the depth. And that is correct. There's a couple other ways to do it. You could increase the width, but it's not as effective as increasing the depth. So increasing the depth is a way to improve this deflection, make it smaller, by bumping up your moment of inertia. Somebody else, what's another thing that we could do to this beam? Increase your E. So what does that mean physically? What? Make it a different material or a better material. So this beam is made out of, if you've got 4,000 KSI, a relative example is that's probably something like a concrete. Okay? Maybe that's not enough. Maybe we got to use something higher grade. Maybe we got to use a steel beam. A steel beam is going to have a higher modulus of elasticity. A higher modulus of elasticity will mean less deflection. So that's another way to improve the design. I mean, you all are engineers, so I'm trying to run this out by you. There are two other options that we could do for this beam that may not be as apparent, but they are very possible. What's another option? Make it shorter. Now, you say change the length, and I think I spoiled it. Would you want to make it shorter or make it longer? You want to make it shorter. Making it longer is only going to make the deflection get even worse. Okay? So making the beam shorter will reduce your deflection. And maybe that's possible, maybe it's not. Okay? What's the other final option? Well, yes, you could change your boundary conditions, but I'm thinking of something a little more basic, something else. All right, it's the most obvious answer. It's so obvious that it's not obvious. Change the load. Decrease the load on the system. Now, one way that you can get about that is to include more components in a system. So, you know, the obvious answer if you're designing, well, the obvious answer in a floor beam system is let's take this room. So there's a column right there, and there's a column right there. So these floor beams have to hold up all the load halfway over to the next floor beam and halfway over to the next floor beam. Just put another floor beam in. Put another floor beam in, that beam is responsible for less load, so it doesn't have to be as big. Okay? And there are similar examples in mechanical engineering. If you're designing let's say a frame or a chassis for a car, put more elements into that frame so that each element picks up less load. And that's a very possible option, okay, in design land. So changing the geometry, changing the loading, changing the material, and changing the section properties of a member are really sort of the four fundamental ways that you're going to improve a design. So that's the big message I'm trying to get across to you as engineers. So, sound good? Yeah, well, yeah. I mean, yes. Negative deflections in this case would indicate downward deflection. If for some reason you had a positive value, it would indicate upward deflection. A lot of times what some folks will do in the beam deflection equation, they'll say the second derivative is negative m over EI so that they get positive answers. I kind of like it like this because then you know negative, oh, it's going down. But of course it's going down. It's loaded this way. So, sound good? All right. Now, what I have shown you just now is the direct method of integration, okay, or the direct integration method to determine deflections in beams. There is another method, and that is the method of superposition. And if I could characterize the method of superposition in one phrase, it would be, if it ain't broke, don't fix it, okay? What I mean by that is this. If you go to one of the appendices in your book, particularly Appendix H. Appendix H has all sorts of beam deflection equations for very, very basic cases, for very fundamentally basic cases. So The idea behind the method of superposition is, let's say you have a problem like this on the bottom, okay? This problem is a simply supported beam, but it has two loading scenarios. It has a uniformly distributed load, and then it has a point load, okay? Well, I propose that this can be split up into two separate problems. We can say that it's this problem and then plus this problem. In other words, if the distributed load causes, let's indicate the same point. Let's say I'm trying to determine the deflection right here. So the deflection at for each beam. So the idea behind superposition is really, really simple. If this load causes 2 inches of deflection and this load causes 1 inch of deflection, how much does the whole thing cause? It's that simple. So the only limit to this method is if you have beam deflection equations available to you. Lo and behold, we do. Enter Appendix H. So if you go to Appendix H, excuse me. You can see, Eric, so here's Appendix H. You can see a number of different fundamental beam deflection equations for a lot of very basic load cases. So the first table lists deflections and slopes of beams that are cantilevered, so like what we did in the last example. So what we've done is, what we did in the last example, I believe it's case 3? No, it's case 4, case 4. So what we did in the last example was a simply supported beam with a point load at the end. Now, just to toy around with this, they're saying that the maximum deflection for the maximum deflection for a cantilevered beam with a point load at the end is PL cubed over 3EI. So for this beam, why don't you go ahead and compute that off to the side? Compute P times L cubed divided by 3EI, and then multiply it by 1728 and see what you get. And lo and behold, you should get about 2.49 inches. I'm curious to see if that works. So the P was 10 kips, the L was 24. Of course, yeah. So the equation in the book derives everything symbolically, whereas what we did was numeric. But in the end, everything works out just fine. Now, excuse me. There are a series of cantilevered beam expressions. So what if you have a point load at the end? What if you have a point load somewhere in the middle? What if you have a distributed load near the end? What if you have a moment at the end? As long as you're determining the deflection at the same point, you can just add those up. You can just find the ones that are appropriate for each section and just add them up. Same thing for distributed loads. So we got triangular loads. We've got cosine loads. Let me be absolutely honest. I have a PhD in engineering. I've never really encountered a scenario with a sinusoidal loading. I have encountered scenarios where you have sinusoidal vibration, where you're vibrating a structure, which should apply to both you civils and mechanicals. You mechanicals, how many machines do you design that vibrate? I think like all of them, you know? So mechanical vibrations are kind of important. Civils, how many buildings do you design that vibrate? Well, if you're in California, all of them. Because what happens in California? Earthquakes. And an earthquake is basically an induced vibration into a structure. So yeah. If you go to grad school, mechanical vibrations is a course that's pretty common for both civils and mechanicals. I took it, and it was fun. It was a lot of math, Okay, so to give you kind of an idea what's going on with this problem, just to explain, and I'm going to do this problem really, really fast because I don't want this to turn into a lot of alphabet soup. I'm probably just going to show you, the plug and chug and then do a lot of the numerical evaluation for you because you have calculators, and I've got to believe you all can do some basic algebra, so I'm not really worried about that. What we have here is a simply supported beam subjected to both a uniformly distributed load and a point load. Okay? And so what I'm asking is, what's the deflection L over 4 away from the support? So I'm basically asking, what's the deflection like right there? Okay? So what I'm going to do is I'm going to handle each of these cases independently. Now, just so we're aware, the deflection there and the deflection right here, you know, there and there, I think we can all agree those are the exact same value because this is symmetric. You know, as soon as those loads move or the geometry of the beam changes, then that isn't going to be the case. But for our problem, this is highly symmetric. So if I go to table H2, the first thing I'm going to do is I'm going to look at table H21. Okay. So table H2, and I'm looking at case number 1. This is a simply supported beam with a uniformly distributed load. Now I look here and I see I've got really 4 expressions. I've got a V prime, a delta max, and a rotation max. Now these are constant values. This is the deflection right at the middle. This is the rotation at the ends. Okay? These two are the expressions as a function of x. Now the difference between V and V prime, V is the deflection, V prime is the slope. Okay? So what we're going to be using is this expression right here. Okay? So for this problem, so we're looking at, what is this, example 27? Okay, so example 27. So we'll say the distributed load. And I'm going to say okay. Somebody on YouTube got a little upset because I started tapping the microphone. So when they watch the videos, they're like, boom, boom, boom. I'm sorry, YouTube. All right. So that equation is minus Wx over 24 EI times L cubed minus 2Lx squared plus x cubed. Okay. Now, if you're wondering where I got that, here I'll even screen capture it so you can see. So I'm using this equation. Okay, so it's the exact same equation. The only thing is I use W's for loads. That's just me. I just replace that. I think it's a little easier to deal with. I don't know. Something about every time I write a Q, I think it looks like a 9, and I don't know. So everything there is just, you know, directly from the equation in the book. And then what we're doing is we're determining the deflection at x equals L over 4. So therefore, if I determine the deflection at L over 4, it's going to be minus W over 24 EI times L over 4 times L over 4 cubed minus 2L L over 4 squared. Oh, nope, you're right, you're right. This, I got that back. This one, this is L cubed. This is L over 4 cubed, right? All right. What I'm going to go ahead and tell you is this. I'm not going to, you know, carry this out, but I think you should be able to do this on your own because this is going to be, you know, L squared over 16. So this is going to be L cubed over 8. This is going to be L cubed over 64. And your Casios can combine fractions and do that for you. So what I'm going to say is this, is that when it's all said and done, you are going to get 19 WL to the fourth over 2048 EI. And I guess I should say negative because it's going downward. All right. So I'm not going to do that for you. I would recommend that you do that. You should go through the practice of combining all that out. I promise you that that's the answer. Okay. If you don't believe me, evaluate it out and see. Okay. But that is going to be the case. If you take 1/24 times 1/4 times the quantity 1 minus 2 over a 4 squared plus a 4th cubed, you will get that. Okay. You'll get 19 over 2048. Okay, that's the case for a distributed load. For a concentrated load, or a point load, I'm going to go to the appendix, and I'm going to see which case do I want to use. Looks like this is my case right here, H2-4, right? Simply supported beam, point load. I can't use this or this because that's the deflection at midspan. This is the rotations at the end. Do I use V or V prime? I use V, right, because I'm looking at deflections. So let's see. That ends up being H2-4. V of X is, and then that ends up being minus Px over 48 EI. And then that is 3L squared minus 4X squared. So therefore, V at L over 4 is minus P over 48 EI. Then we have L over 4, 3L squared minus 4L over 4 squared. And when you chug that out, what you will end up getting is minus 11 PL cubed over 768. And again, you have calculators, you can compose those fractions and do that pretty easily. So therefore, V at L over 4 is going to equal, and the way I'm going to write that is this. I'm going to say, because I think the negatives will make it a little more complicated, I'm going to say 19 WL to the 4th over 2048 EI plus 11 PL cubed over 768 EI, but I'm going to indicate that that deflection is going downward. What do you think? Any questions? All right, if there are no questions, you should be well equipped to handle your next homework assignment, because your next homework, or your homework 6, I mean, because your homework 6 is 2 problems on deflections. One of them is a traditional deflection problem like what we did in the previous example, and one of them superposition like we just did here. So it's pretty straightforward. After this, like I said, so Tuesday we're going to cancel class. I'm not going to be here. Thursday we're going to get into stress analysis. So stress analysis, I'll go ahead and tell you, it's going to actually incorporate a good bit of trig. Remember, up until now we've been cutting our sections, samurai sword, like we've been doing a judo chop, but we're going to try and do maybe a ninja chop. Now, you don't go, here's the thing, you don't go karate chopping while kung fu kicking. There goes your leg. What's that? You don't ninja, nobody don't need ninja. So if you don't get the reference, Just Google West Virginia Ninja. Is that what is it? Would that pull it up? Get right about like that, and a ninja star. You didn't think that that would get brought up in an engineering course, did you? I mean, there goes your leg. It's simple. I mean, that discussion has a lot of connotations to engineering. There's dynamics, There's ethics. Don't go ninja nobody that don't need ninja. But in all seriousness, when we look at stress analysis, what we're going to be doing is instead of cutting sections normally, we're going to be cutting sections at an angle. So we're going to be generating normal stresses and shear stresses along a given plane. So how do you compose those stresses and determine worst case scenarios? Because what we're ultimately trying to find when we do stress analysis, and I'll sort of call it this, but what we're ultimately trying to find when we do stress analysis is we have a scenario where instead of just having torsion or just having axial load and just having bending, what if we have all this stuff? What if we have a section where we're bopping it, twisting it, and pulling it, okay? And then we've got normal stresses and shear stresses and all sorts of different, scenarios. I propose to you that in those scenarios, you're actually going to get different stresses the way that you cut. Like you'll get some stresses this way, you'll get some different stresses this way, and some different stresses this way. And so stress analysis is trying to determine the worst case scenario so that you generate worst case normal stresses and worst case shear stresses, and it tells you as the engineer whether or not this is going to be a sufficient design. But in order to do that, I'll go ahead and tell you our next lecture next week, we're going to break out trig. And by trig, I mean, remember all those, the sine of 2 theta is 2 times the sine of theta times cos, all those trig identities that you forgot, 6 years ago. Well, they're coming up again. So don't worry. I try and make it easy on you. And I'm not going to make you remember these, identities for an exam or anything. It's coming. So just be aware of that. All right. That's all I've got. I will see you all next Thursday. You guys have a wonderful weekend and a wonderful break from deformables. We'll see you.